In this lecture, we will discuss power analysis, which is a very important tool and approach we can use when it comes to inferential statistics, but one that's not often employed. So we'll start off by talking about what statistical power actually means, and then we'll talk about some general purposes for why do we actually do a power analysis. And we'll finish up by talking about different tools and techniques you can use to conduct a power analysis. So let's start with what a power analysis actually is. Well, first, when you hear statistical power, or just power for short, it refers to the fact that given a particular analysis or design, the probability to detect a true association or difference in the underlying population, or in other words, our ability to find an effect that actually exists. Now, a power analysis is the process we use to determine the probability of an analysis or a design in its ability to detect a true association or difference in the underlying population. So there's four important elements or components of statistical power, or that fall into, more broadly, a statistical power analysis. And these are the sample size of your study, which is represented by N, the effect size. So if you think about effect size, these are those standardized metrics such as Cohen's d, a correlation coefficient, Cohen's f, the r-squared value, and so on, as well as two other elements called alpha and power. Now, alpha is represented by that Greek letter alpha, and power is represented by 1 minus beta, so the Greek letter beta. So in order to do a power analysis, you need to know at least 3 out of these 4 elements, and you can then estimate the 4th one. Or you can guess with some of them as well, even if you don't know them for sure. So when it comes to type 1 error, which I'll explain in a second, this really corresponds to the alpha level that we set. And if you remember, that alpha level is really about what that threshold is going to be for our p-value, our test of statistical significance. Commonly, we set it at a two-tailed alpha of 0.05. And so that refers to what we call type 1 error. Now, the beta in the power, so remember power is represented by 1 minus beta, beta by itself relates to type 2 error. And so power analysis is really about addressing type 2 error, while also recognizing the sacrifices you might make when it comes to addressing type 2 error in relation to what type 1 error might become. To understand type 1 and type 2 errors, it's helpful to look at this table here that's presented. And in particular, I'll point out 4 different quadrants that are important for understanding what a type 1 error is versus a type 2 error. And this is really centered around this idea of making correct or incorrect statistical decisions. And so if you notice at the top of the table, there's the truth in the population. And so remember, with inferential statistics, we're talking about making inferences based on what we find in a sample about the underlying population. And so what we're assuming is that in the population, the null hypothesis is either true or it's false. If the null hypothesis is true, it means that, let's say, there's no difference or no association in the underlying population between these two variables, let's say. Now, if the null hypothesis is false, this is essentially saying that there is some difference or association between the two variables. Now, the other part of this table that corresponds to the rows is your actual sample findings. What did you find by collecting data and running your inferential statistics? And so there's really, if we're using null hypothesis significance testing, there's really 2 conclusions you'd come to for a particular investigation of an association or difference and whether they exist. And the first is that you would fail to reject the null hypothesis. And so what this means is that you would conclude that actually there doesn't seem to be any evidence that there's a difference or association present based on what you found in your sample. If you reject the null hypothesis, this would mean that you're concluding that there is some kind of difference or association in the sample that you believe to be underlying in the population as well. But really, when it comes to making statistical decisions, we're weighing, well, what is the truth in the underlying population, which we'll never fully know, and what did you find in your particular sample? And so let's start with the first quadrant here. So if we make a correct statistical decision, it might be that in the underlying population, the null hypothesis is false. And what that implies is that there is some difference or association between the two variables or more variables that we're interested in. And in our sample, we actually correctly rejected the null hypothesis, implying that the null hypothesis is false. So in other words, we found in our own statistical analysis based on our sample that we needed to reject the null hypothesis that there is no difference or association, and thereby concluding that yes, there is some kind of association or difference, and this corresponds to being true in the underlying population, meaning that the null hypothesis is false in the underlying population, so this would be a correct statistical decision. Now, another type of correct statistical decision according to this model is in the instance in which the null hypothesis is actually true, which would mean that there is no difference or association between the variables. Now, in our sample, if we fail to reject the null hypothesis, this would be a correct decision, assuming that in the actual population, the null hypothesis is true. So in other words, we are concluding that we did not detect any difference or association between the variables in question in our sample, and it turns out that in the underlying population, the truth is that, yeah, there is no difference. In other words, the null hypothesis is true. So that'd be the second type of correct statistical decision that we'd make. Now let's talk about the different errors that we can make, and specifically type 1 and type 2 error. So type 1 error would be that in the underlying population, the null hypothesis is true, which means that there is no association or difference among these variables. Now, if we were to, however, in our sample, reject the null hypothesis that there is no association or difference, would mean that we're actually concluding that there is a difference or association between these variables, when in reality, that doesn't exist in the underlying population. We've made an error here. We've made a mistake. And so this is what's called type 1 error. So type 1 error is when you find something in your sample to be statistically significant that actually doesn't exist in the underlying population. It's maybe just due to random chance or some error that you detected, but not anything that's actually real. Now, the other type of statistical decision-making error is what's called the type 2 error. And so this is when in the underlying population, the null hypothesis is actually false, meaning that there is some kind of association or difference between the variables or among the variables. However, in our sample, based on our statistical analysis, if we, based on our test of statistical significance, fail to reject the null hypothesis, meaning that we conclude that, well, there's no evidence that we found that there is a difference or association between these two variables, we're actually making an error here, and specifically type 2 error. In other words, we failed to detect a relationship that actually exists in the underlying population. Now, both of these types of errors are important, and we'll talk about in a second why it's kind of a give and take. So if you really want to focus on reducing type 1 error, by the process and how you actually calculate power, it's going to affect your type 2 error, and you'll have to sacrifice some on type 2 error. And conversely, if you really want to address type 2 error, you're probably going to have to relax your type 1 error constraints that you might have in place. And so note here too in these tables that by convention, I'm displaying the hypothesis or the null hypothesis is conveyed by H sub 0. Now, if you see H sub 1, this refers to the true alternative hypothesis, which is usually what we're actually talking about in practice. You can think of this as your research hypothesis. So instead of saying the null hypothesis being that there's no difference or association, the true alternative hypothesis would be whatever that we're actually hypothesizing in terms of whether there is an association or there is a difference and it's in this direction or of this magnitude. So let's break this down visually, and this is sometimes a helpful way for understanding these statistical decisions and specifically what affects type 1 and type 2 errors. And so what you're looking at here are two sampling distributions of means. And so you have the sampling distribution for the null hypothesis, which is H sub 0. This is the one on the left. And then you have the sampling distribution for H sub 1. And this is for the alternative hypothesis, the true alternative hypothesis. Now you notice the dotted lines that go through each one of these distributions. At the bottom you'll see mu sub 0. Mu sub 0 corresponds to the mean of that sampling distributions of means for this for the null hypothesis, and mu sub 1 corresponds to that mean for the alternative hypothesis, the true alternative hypothesis for this sampling distribution of means. Okay, so now let's talk about the critical value. So a critical value is going to correspond to whatever your alpha level is set at. And so an alpha level is going to be the threshold by which we evaluate whether or not our probability statistic or a p-value can be treated as being statistically significant or non-significant. And so this p-value or alpha level that we set here will correspond to some kind of test statistic, maybe a t statistic or something like that. And so let's assume that we set the critical value here, and then because we've set that critical value, that implies that we've now set our alpha value, which has to do with our type 1 error. And notice that the alpha value is corresponding to that sample distributions of means for the null hypothesis here. And so that's shaded in blue and represented by that Greek letter alpha. And so what this is saying is, what is the probability that we find a value that's as extreme in terms of the critical value or more extreme, and that is actually in error? So it really still means that we've actually falsely concluded that we should reject the null hypothesis, when in reality that's just actually a random occurrence, and it means that there actually isn't any truth in the underlying population, that there is actually an association between the variables or a difference between the variables or whatever the question might be. Now, by association, beta or type 2 error is very much related to alpha. And so here you can see in green shaded in with the Greek notation of beta is our estimate of type 2 error. And so if you were to increase the alpha level, it would actually decrease the beta level. So there's this kind of give and take here because you're moving that critical value back and forth. Now notice here that the Greek numeral b and that type 2 error actually corresponds to the true alternative hypothesis sampling distributions of the mean. And so what you can see here is that the more green that you see showing there, it means the less likelihood that we have to detect something that actually exists there. So we want beta to be as small as possible, and we want alpha to be as small as possible, and this is where there's that give and take. If you increase alpha, you're decreasing beta. If you increase beta, you're decreasing alpha. In other words, type 1 and type 2 error are inextricably linked in this context. Okay, so the next concept is this idea of statistical power. So type 2 error is a function of statistical power, or just simply power, because remember, power is simply 1 minus beta, or 1 minus the type 2 probability. And so this is all the yellow that you see shaded in here in the sample distribution of mean for the true alternative hypothesis here. So ideally we want as much yellow as possible because this is our power to detect something that actually exists, whereas we want to also minimize the amount of blue that you see there because that's our type 1 error, which is the probability that we conclude that something exists that doesn't actually exist in the underlying population. So again, you kind of have this give and take here. And the further apart these distributions are going to be, which means we have a larger effect size, the more likely we're going to have higher statistical power. And also, the greater the sample size we have, it means that we also tend to have less variation around those means too. So you can imagine these distributions getting skinnier, meaning that we're going to have more confidence in our ability to find differences. And you can imagine how that would affect the areas that are shaded as alpha for type 1 error and beta for type 2 error. Okay, so why is it important to address type 2 error? Historically, we were really concerned when it came to statistics about type 1 error. In other words, we were very concerned about falsely concluding that something exists when in reality it doesn't exist in the underlying population. But in more recent decades, we've grown more concerned also about type 2 error, which is the failure to detect something that actually exists in the population. And so this can be really problematic too. So we want to make sure that we have adequately powered studies and analyses so we can actually detect things that actually exist. But at the same time, we don't want to falsely conclude that something exists when in reality it doesn't exist. Now, if you're really curious about learning more about type 2 error and by association statistical power, I recommend checking out this study or this article that was published by Fiedler and colleagues in Perspectives on Psychological Science. Now, if you're also interested in learning more about power in general and why power is important and what are the constituent parts of statistical power, I recommend reading these two articles by Jacob Cohen from 1992. The first is published in Psychological Bulletin called a Power Primer or Power Primer. And the second one was published in the Current Directions in Psychological Science, and it's called Statistical Power Analysis. Both are very accessible and great resources for understanding what power is and why it's important. So now let's focus on some general purposes, why we care about statistical power in practice. We've just talked about theoretically why it's important. Let's talk about it in practice and why we would actually do a power analysis. Well, there's really three different reasons. You could probably come up with more, but here are the three that I think are most important. The first reason, or the first general purpose for conducting a power analysis is that before collecting data, in order to test a hypothesis or investigate a research question, you might use a power analysis to determine the necessary sample size to achieve sufficient statistical power. And by convention, sufficient statistical power is usually about equal to or greater than 0.80. Although that's just like an alpha value of 0.05, it's not hard and it's not necessarily a set and immutable value. Rather, really depends on what your goals are. If you make power higher, let's say 0.95, it means that you're going to have more confidence or you're going to have a higher probability that you can detect an effect that actually exists. But remember, the higher the power you make, it also means that you're also going to potentially be increasing your type 1 error. Okay, so now let's talk about the second purpose, and that is that before collecting data, you might use a power analysis to determine the minimally detectable effect size, or the MDES, for a range of different sample sizes. So trying to figure out, okay, what is the minimal effect that we think we'll find, and then what are the different sample sizes we might need, and what are the different power levels that those might result in. And the third general purpose is that after collecting data, so this is more post hoc in nature, determining whether, you might use a statistical power analysis to determine whether the design or the analysis and the sample size that you employed had sufficient power to detect relationships if they were to exist in the first place. And so when it comes to the first general purpose, it's really about this idea of knowns and unknowns as well as best guesses. So when it comes to using a power analysis to determine the necessary sample size to achieve sufficient statistical power before you actually collect or acquire data, what you know is alpha and your power. So you can set those values ahead of time. So you might say that alpha is 0.05 two-tailed, and you might say power is, let's say, 0.80 if you're going to use a common convention. So those are knowns. But then you'll have to actually guess what is the effect size that you expect. Now, there might be prior research that's published in peer-reviewed journals you can use to look to understand, okay, what have other people found with this relationship? Or you might have other internal relationship or information you can use based on your internal studies or research that can point you in a good direction in terms of what to expect with that effect size. But it really comes down to a guess. Now, the unknown that you're actually going to be estimating here is the sample size. So what sample size is going to be required to have sufficient statistical power? The second general purpose is that before collecting data, you can use a statistical power analysis to determine the minimally detectable effect size, or MDES, for a range of sample sizes. So in this context, what is known are the alpha levels, the power, and the sample size, or rather, you're going to give a range of sample sizes, and the unknown is the effect size. So let's say for the knowns, you say that alpha is going to be set at the conventional 0.05 two-tailed test, and that power is going to be set at the convention of 0.80, and sample size, let's say you're going to give a range of 100 to 300 people. Well, then the unknown is, what is the minimally detectable effect size for each level or for each sample size? And you can actually develop a power curve in this way, and you can figure out, okay, well, what is it that we need to aim for here at each sample size? What can we actually detect in terms of effect size at each sample size along that continuum of the range? So now let's focus on this third general purpose, which again is after collecting data, so post hoc in nature. You can use that statistical power analysis to determine whether the design or analysis and the sample size you acquired had sufficient power to detect relationships if they were to actually exist. So after you've collected all your data, were you even in a position to actually detect a meaningful relationship if it actually existed in the underlying population? If you weren't, that's when we'd say you were underpowered. Your study was underpowered, your investigation was underpowered. You just didn't set yourself up for success. So in this context, for this general purpose, the three knowns are your alpha, your sample size, and your effect size. So you know what you set your alpha level at, let's say 0.05. You know what your sample size is because you already acquired the data, and you know what your effect size is because you already have the data. Now that's all that's left to estimate is the power. So what statistical power level did you have? Again, ideally we'd like to see 0.8 or higher, but that's just a convention. The closer you can get to 1.0, the better. So 0.9, 0.95 and better would be really good statistical power. So you can be pretty confident at that point that you had adequate power to detect something that actually existed in the underlying population. So how do you actually carry out a power analysis? Well, fortunately, there's a number of tools, packages, and platforms that you can use, some of which are freely available that I'm going to go over right now. So just remember, though, before I get into this, that like anything, it's a garbage in, garbage out. So you'll notice that as I was talking through the general purposes of a power analysis, that a lot of times there's going to be some best guesses or things that you're going to have to estimate, especially when it comes to effect size. So what is the minimally detectable effect size? What kind of effect size can you expect before you've actually collected the data? Well, you're making a guess here. To the extent that you make a really garbage estimate on the effect size, doesn't matter if you throw that into the power analysis, you're not going to get good information coming out on the back end. So it's important to remember that first. So I'm going to talk about these 5 different tools and techniques that you can use for power analysis. Again, some of these are freely available. So let's start with GPower. So GPower is a free download, and I provide the link here. It's very user-friendly because there's drop-down menus and things like that. In fact, there's even documentation in behavioral research methods that Fowle and colleagues in 2007 and 2009 published articles in which they go over the use of GPower. And so this is a really, really useful set of documentation that you can use to understand how to apply GPower to your own studies. This is a great entry point if you just want to play around with the concepts of GPower. Again, in terms of the graphical user interface, it's very simple. There's drop-downs, and you get with some decent graphics coming out of it. And so you can see in the left panel, the screenshot, that we actually have those 2 sampling distributions of them around the means are actually presented there, and you can see those, as well as you'll notice some open blanks here in the form where you can put in your estimate for power, your alpha level, and so forth, and your effect size. And you'll notice in the right panel here that we actually have a power curve, and you can see that the power curve is displayed here where you have on the x-axis the total sample size you could expect, and you see a range here, and then you have on the y-axis the statistical power that you can expect, and then 3 different, if you look at the legends, 3 different levels of effect sizes. So let's say small, medium, and large, and you can see that when you have a larger effect size, it's going to be easier to get to adequate levels of power quicker in terms of having lower sample sizes needed compared to smaller effect sizes you could expect, where you'll actually need larger effect sizes to detect those effects that exist in the underlying population. Now, the second platform is called Optimal Design. It's also a free download, and I provide the link here. Now, it's great for experimental designs, person randomized trials, cluster randomized trials, and even meta-analyses. And there is some documentation here by Browdenbush and colleagues from 2011, and you can find that there through that link, and they'll walk you through what optimal design software is used for and how it can be useful in multi-level and longitudinal research. And here's some screenshots from Optimal Design. Also, it's a nice, easy, click-through, user-friendly interface with drop-down menus. Now let's talk about a couple of R packages that I found to be very helpful when it comes to estimating power. The first one is PWR, or power, and all lowercase, and it's a free R package like all R packages, and you can find that through the Comprehensive R Archive Network, or CRAN, and download that directly and install it into your R platform. Now, this is great for designs that require analyses such as t-tests, one-way ANOVA, chi-squared tests, and so forth. And there's really good documentation on this if you go to the link that I provided there, or just Google PWR, R, and CRAN, for example. And there's also some additional information too by Champollion that you can find in which they go over some of the basic functions of power analysis using this package. And so I provide the link for that as well. There's also another R package called BMEM, or BMEM, all lowercase, and this is again another free R package. This one uses Monte Carlo simulations, and this is great for designs that involve some kind of mediation, where a mediation is this idea that you have, instead of just x leading to y, you have this third variable, let's call it the mediator, that transmits the effect of x to y. And so this is a little bit more complicated of a design, and fortunately someone developed the BMEM package to tackle these mediation type designs that you might use in mediation analyses. And again, Behavioral Research Methods published an article by Zhang in 2014. Behavioral Research Methods has a number of helpful articles on different types of platforms like these. And in this one, they actually work through how to actually use the package in the context of investigating statistical power for mediation models. Now, there's also a pay-to-play package called M+. M+ is actually really outstanding. It's syntax-based. It does require the purchase of a user license. They do have a student license too that you can use, but it's more limited in its capabilities and functions. Now, M+, like the BMIM package from R, uses Monte Carlo simulations, but it can tackle more complex types of designs even than the BMIM package. So not only can you test mediations, but you can also test moderated mediation models, or what are known as conditional indirect effect models, where the indirect effect is really X's influence on Y via the mediator variable. And also you can investigate these types of models in a multi-level framework where you have both a within and a between level, or a level 1 and level 2, such as individuals nested within teams at work, or time periods, let's say time 1, 2, and 3, nested within individuals. And the documentation for M+ is really outstanding. There's a lot of great user help forums, it's particularly the one that's hosted by the M+ people. It was developed by Muten and Muten, and the user guide has a lot of great examples you can work through. But this is another way, if you have more sophisticated designs, to actually estimate statistical power. So in this lecture, we described what statistical power, or just simply power, actually means. And really it comes down to that probability that we can actually detect something that actually exists in the underlying population. So this is something that's very important to consider. We want to make sure we're setting ourselves up so that we can actually find something that actually exists. Now, we also talked about what a power analysis is, or more formally, a statistical power analysis. And we diagnosed 3 different general purposes that you might use a power analysis for, 2 of which are a priori, or before you collect the data, and the third one is post hoc, so after you collect the data. And then I reviewed some common tools and techniques. That wasn't a comprehensive list, but those are some of the ones that I've used in the past that can be really great and useful for estimating statistical power. So this wraps up the lecture on power analysis.